Mark your own. So what are you going to see on the written section of your test? You can definitely expect a work question. Maybe two, maybe one, how much work to lift something in orbit? Sorry, bad choice of words, Mr. Dick. How much work to lift something into outer space but not put it in orbit? That means you can say the change in kinetic energy is 0. I think we did the one like that on quiz number 1. Or you know what? You're going to have how much work to put something in orbit. So how am I going to solve this? What's this question asking me to find, Sophia? How much work? This is not going to be conservation of energy, G, because it asked how much work. I'm going to start out by going, okay, work equals the change in potential plus the change in kinetic. If we're not in a stable orbit, if the question just says we're lifting it up, but it implies we can let it drop, then you can cross out the change in kinetic. But we are in a stable orbit, so we have to also have added some kinetic energy to it. Let's find change in potential first. The change in potential, what's change in anything? So it's going to be final minus initial, negative big G, big M, little m, all over our final, minus negative big G, big M, little m, over our initial. Are we in orbit around the space or around the space? Are we in orbit around the Earth or around the moon? I'm thinking, because typically when we did these questions for Earth, we ended up in the 10 to the 10th, 10 to the 11th range. I suspect it'll be less energy than that. Should be. Let's plug in our numbers here. It's going to be negative big G. What's the mass of the moon? 7 something, I think. 7.35 times 7.35 times 10 to the 22. Mass of the satellite is 1,600 all over. This is above the surface of the moon, so I'm going to need to add the radius of the moon. So it's going to be 2 times 10 to the 6th plus, it's 1 point something, but I can't. Somebody, I can't remember, was in this class or another class. Mr. Duke, how do you know when to go above and when do you add the radius of the planet that you're orbiting and when do you not? If it's above, they've given me an altitude. They've given me that distance away from the planet. Plus, same thing times same thing times same thing. Our initial, I guess, must have just been the radius of the moon. So let's crunch some numbers. It's going to be, there's just no short way to do this. Negative 6.67 times 10 to negative 11 times 7.35 times 10 to the 22 times 1,600 divided by bracket 2 times 10 to the 6th plus 1.74 times 10 to the 6th. Look for typos. I think that looks right, Mr. Dewick. Negative 2.0973 times 1, 2, 3, 4, 5, 6, 7, 8, 9. 2.0973 times 10 to the 9th. Plus, same thing, but I can ditch the negative, and it's just going to be radius of the moon. And I get 4.508 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8, 9. So it's going to be negative 2.0973 times 10 to the 9th plus answer button. And the change in potential is 2.4107 times 10 to the 9th. 2.4107 times 10 to the 9th joules. I'll come back to that, but I'll put a box around it because I'm going to need it. I also need to find the change in kinetic energy. That's going to be a half mv orb squared minus a half mv initial squared. We'll launch from the top of the pole, either south pole or north pole of the moon. I can't say Santa's workshop. I'm not familiar enough with Marvel or DC. Does any of the superheroes have a base on the moon at all? Okay, so we'll just pretend we're launching from the North Pole of the moon. How do they know what the North Pole of the moon is? Have I told you how they find north and south on planets, how it's defined?
It's something with your thumbs pointing and you curve it.
You curl your fingers in the direction the planet spins, the fingers of your right hand in the direction the planet spins, and your thumb points north. Venus spins in the opposite direction of all the other planets, which is why its North Pole is on what we would consider the bottom. Because most planets don't have a magnetic field, so we had to come up with some way to define what north was, and that works for Earth as well. 0.5 times 1600 times 1.145 times 10 to the third. Don't forget the squared. The change in kinetic energy is going to be 0.5 times 1600 times 1.145 times 10 to the... Why did I put a times 10 to the third in there, Mr. Duick? I don't think... Oh, yeah, okay. It's 1,145. I'm okay with that. Squared. Oh, I'm good. I get 1.0488, 1, 2, 3, 4, 5, 6, 7, 8, 9, 1.0488 times 10 to the 1.0488 times 10 to the 9th joules. Okay. The work is going to be 4107 times 10 to the 9th plus 1.0488 times 10 to the 9th. It's going to be 2.4107 times 10. No. Positive.
Oh.
It takes energy.
Sorry, no,
It takes energy. Okay. As long as you get it right, I won't be fussy, but taking a risk. Plus answer button. Y'all get 3.46 times 10 to the 9th? If you got that, 7 out of 7. Now, how would I give out part marks? That's a good question. I need to see the whole page here. So I would probably go something like this. 1, 2, 3, 4, 5. Yeah. 1 mark if I saw that, 1 mark if I saw that, 1 mark if I saw this number, 1 mark if I saw this number, 1 mark if you got the change in potential correct, 1 mark if you got the change in kinetic correct, and 1 mark for the answer. Something like that. Yep.
I would assume part works if you didn't calculate change potential, just all three numbers. You just add it all.
Did you get the right answer?
Yes.
If you get the right answer, 7 out of 7. Okay. Right? That's how I start out, and then I go looking for part marks. The risk you're taking is if you get it wrong and you don't show me all your steps clearly, then I can't give you the part marks that I'd like to give you. Right? Number 2. They didn't give me the orbital speed. Jeez. Okay. How much work? It's going to be change in potential plus change in kinetic. Change in potential is going to be negative big G, big M, little m over R final minus negative big G, big M, little m over R initial. It's going to be negative big G. We're around the Earth again. 5.98 times 10 to the 24th. We're around little m, 3,200, not around it. All over. Oh, they gave me an orbital radius at least, so 8.3 times 10 to the 7th. Plus, same thing times same thing times same thing. All over 6.38 times 10 to the 6th. It's going to be some heavy-duty typing. Okay. Negative 6.67 times 10 to the negative 11 times 5.98 times 10 to the 24th times 3200 divided by 8.30 times 10 to the 7th. I stuck the 0 there because in the next one I wanted to be able to fit 6.38 without having to retype stuff. Looking for typos. I missed a decimal up there, so let's insert that, Mr. Dewick. Good, 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 good. I think that looks good. That's a pretty high orbit. This should take a fair bit of energy. Yeah, times 10 to the 10th. Negative 1.5378. Is that right? Plus, if we start out on the Earth, we're going to be positive, and it'll be 6.38 times 10 to the 6th. 2.0006. 2.3 zeros and a 6. 2.3 zeros and a 6 times 10 to the 11th. So the change in potential energy is going to be negative 1.5378 times 10 to the 10th plus answer button. No typo, no typo. 5378 looks good, looks good. Do you get a change in potential of 1.8468 times 10 to the 11th? 1.8468. 1.8468 times 10 to the 11th joules. And oh heck, just for giggles, where's my work? There is my work. No, I don't want that. I want the whole calculator, Mr. Dewick. Kind of like that. Anyways. Now let's find the change in, oh, you know what? Am I going to have enough room? Maybe I will. Change in kinetic. The change in kinetic is going to be a half mv orb squared minus a half mv initial squared, although we said we're launching from the North Pole. They didn't give me v orb. You know what? I'm going to need this room after all, because I'm going to need to say over here, gravity is what's pulling me in a circle. Big G, big M, little m over r squared equals mv squared over r. Hey, one of the r's cancels, one of the little m's cancels. That's v squared. Okay, so I can say the change in kinetic energy is going to be a half little m, big G, big M over r. It's going to be 0.5. What was little m, Mr. Dewick? 3200. Big G, 6.67 times 10 to the negative 11. Big M, 5.98 times 10 to the 24th. All over little r, 8.3 times 10 to the 7th. The change in kinetic is 0.5 times 3200 times 6.67 negative 11 times 5.98 times 10 to the 24th divided by 8.3 times 10 to the 7th. So one way to do it would be this. And I got 7688, is that right? Or if you have a calculator that lets you go back multiple lines, I actually remembered, hey, this is going to be half of that potential energy, but positive. Because those are all the same numbers I just typed in. So if I take that number right there and divide it by 2, I also get 7688. 9.8. So either of those methods is fine. That's where that little handy shortcut can save you a bit of time. But again, Alexis, did I need it? No, it's a handy shortcut. 7.689 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8, 9. 7.689 times 10 to the 9th joules. And so, final answer, the work is going to be, forgot to put a box around this one, I had to go hunting for it, 1.8468 times 10 to the 11th. Is it 10 to the 9th? Let me double check. 1, 2, 3, 4, 5, 6, 7, it is. Okay. Plus 7.689 times 10 to the 9th. Wait, the potential energy is dominating this equation. The kinetic is only going to make a little blip on the answer. 1.8468, scientific notation button, 11 plus answer button. Hey y'all, did you get 1.92 times 10 to the 11th? Whew. If you got that, 7 out of 7. Otherwise, I would probably do something like this. I would give you 1 mark if I saw that number, 1 mark for that, 1 mark for that. I would give you 1 mark if I saw that you'd realize gravity was pulling us in a circle, 1 mark for finding the change in kinetic energy. That's 1, 2, 3, 4, 5 marks. I would give you 1 mark for the answer. That's 6 marks. I'd probably give you 1 mark for recognizing that we had to use the work energy theorem. Something like that. Wow. These are a lot of work, no pun intended. Now, I'm not going to give you one on your test where I don't give you the orbital speed. So what you're going to see on your test is something like number 1, not like number 7. Sorry, not like number 2. Okay? You are going to have an escape velocity question on your test. So escape velocity, first of all, is this question asking how much work? So don't be writing work equals change in plus change in. Are we in orbit if we're attempting to escape a planet? So don't be telling me gravity is what's pulling me in a circle. What's our third option? There's a change in height, change in speed. This is going to be conservation of energy. Except, are any of these 0? In our strange approach, we're going to let that be 0 because out at infinity, you have no potential energy. And Hannah, we want to plan this so perfectly because as we coasted, we'd be slowing down because gravity would be pulling on us, slowing us down, slowing us down, slowing us down. We want to come to a stop right when we reach infinity. We want to do this so perfectly that we have no extra energy left over. So we get this. A half mv initial squared plus negative big G, big M, little m, all over R initial equals 0. Or I typically wrote this as a half little m v initial squared equals big G, big M, little m over R initial. And what's kind of nice is little m cancels. That's good because they didn't give me the mass of any spaceship. I want to get the v by itself. The escape velocity is going to be, it looks like 2 big G, big M over R square root. It's going to be the square root of 2 big G. What was the mass of the planet, Mr. Dewick? 3.14 times 10 to the 30th. Ooh, that's almost the size of a star. Or maybe I just think of myself as a shining nothing. Okay, 3.14 times 10 to the 30th. Big ego, Mr. Dewick. No kidding. Planet-sized, literally. 2.72 times 10 to the 7th. 2 times 6.67 times 10 to the negative 11 times 3.14 times 10 to the 30th divided by 2.72 times 10 to the 7th. You know what, Mr. Duke? Why don't you just go square root of that? You can do that in one step now. 2 big G, big M over R. Looking for typos. Do you get an escape velocity of 3.92 times 10 to the 1, 2, 3, 4, 5, 6? If you got that, 7 out of 7. Otherwise, I would probably give up part marks like this. I would give you 1 mark if you wrote conservation of energy. I would give you 1 mark for recognizing both of those are 0. I would give you 1 mark if I saw that. I would give you 1 mark if I saw that. 1 mark for the escape velocity equation, 1 mark for the numbers, and 1 mark for the answers. That's 7, 1, 2, 3, 4, 5, 6, 7. Yes, it is. Number 4. Ooh, asteroid impact. Again, is this question asking how much work? Then don't be writing work equals change in plus change in. If we're impacting the planet, are we in a stable orbit?
No.
Don't be saying gravity is what's pulling me in a circle. Okay. Conservation of energy. Are any of these 0? How could I make one of these 0? I could say the asteroid started at rest. That would make that 0. Or I could say we started from a very, very, very far distance away. That would be my way of saying, let's pretend we started at infinity, and you could let the initial potential be 0. But sadly, nothing. A half little m v initial squared plus negative big G big M little m over R initial equals a half little m v final squared plus negative big G big M little m all over R final. Yes?
You could also make potential final.
You're cosmic. You can't, there's not many shortcuts here. What were you going to suggest?
Impacting the center of the Earth like a black hole singularity.
No, well, that would have to somehow go through the planet. Yeah, that doesn't. The physics breaks down enough that I wouldn't feel comfortable doing that as a question because the physics breaks down. So I wouldn't. But I can certainly do this. What am I trying to find? So what could I ask you to get by itself? For a conservation of energy question, one option is to start on Earth. That would make your initial on Earth over here, and fire a rocket straight up and ask how high will it get. That would ask you to find that. How would you get that by itself? I wouldn't. I would first of all move everything else over, turn it into one number, and then you'd have that equals negative big G big M little m over R final, and then stuff moves diagonally. I would multiply by R final and divide by the number, and I'm good to go. So that's how I would get one of the R's by itself. I would not try and do it algebraically. It's just way too difficult. You can do it, but it's a pain. If you're bored, see me during a flex and I can show you how, if you really like to get stuff by itself, you can. Here, I'm getting the V by itself, so I think what I would do is, you could multiply by 2 to clear the 1/2. I chose not to. I said, okay, this is going to be 0.5 V initial squared plus negative big G big M over R initial plus, in fact, instead of plus negative, I wrote minus right there, and here I wrote plus big G big M over R final. That equals 0.5 V final squared. And I'm going to start crunching numbers right now. 0.5 V initial, 1.37 times 10, 1.37 times 10 to the 4th, don't forget the squared, minus big G, 5.98 times 10 to the 24th. All over, where do we start? It's from the center of the Earth, so it's a radius, 2.2 times 10 to the 7th, plus, same thing times same thing times same thing, all over 6.38 times 10 to the 6th. How come that's in the final location? Because we're ending up on the Earth. That equals 0.5 V final squared. So 0.5 v final squared equals this first number, 0.5 times 1.37 times 10 to the fourth squared. I get 93845,000. You know what? 93845 and 3 zeros. I'll just write it. 93845 3 zeros. And then take away big G, big M, 2.2 times 10 to the 7th. Looks good. I get take away 1.813 times 10 to the 1, 2, 3, 4, 5, 6, 7. 1.813 times 10 to the 7th plus same fraction, but on the bottom I'm going to have 6.38 times 10 to the 6th. And I'll get 6.252 times 10 to the 1, 2, 3, 4, 5, 6, 7. 6.252 all right, 93845 1, 2, 3 minus 1.813 times 10 to the 7th plus answer button. I get 0.5 v final squared equals 1.382 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8. 1.382 times 10 to the 8th. And now I would either divide by 0.5 or times by 2, square root of that. Do you get 16,600? Whew. Does anybody remember what escape velocity for the Earth was? Basically, asteroids, if they're coming from outside of our solar system, they must hit us faster than that because they must have had enough energy to initially leave. They'll bring all that energy back. So they'll hit us with at least 11,200, if I'm making up good questions. If you got that, 7 out of 7. Otherwise, how would I give up part marks here? Good question, Mr. Dewick. Whew, 1, 2, 3, 4. That's a lot of work. I would probably give you 1 mark if I saw conservation of energy. I'd probably give you 1 mark if you got the 0.5 v squared by itself. I would probably give you 1 mark for that, 1 mark for that, 1 mark for that, 1 mark if I saw that, and 1 mark for the answer. Something like that. Can you give yourself a score out of 28, please?